Okay, so if I have this summation a sub n starts with 1 or 0, goes to infinity, this will not converge unless a sub n, that sequence must go to 0, the limit of that. Now, it still doesn't tell you anything. It's just saying, I don't know. It's just saying that if I look at the sequence, those n terms have to go to 0, so that basically when n gets to be really big, you're not adding any more in. But it's not sufficient. It's called necessary and sufficient. This is necessary for the sequence to converge. If I try to add up 1, n equals 1 to infinity, that will not converge because I keep adding 1 on at the end. That keeps getting bigger and bigger and bigger. So this, when you do the linear sequence, the sequence has got to be going to 0 for the series to converge, but it's not a guarantee. It's a necessary condition, but it's not sufficient to get the series to converge. Those are big math words, necessary and sufficient. Okay, so that's our first convergence test. The second one is the geometric series. The third one is going to be collapsing sums, which we're going to do today. It's going to take all hour to get through all this. And kind of neat stuff. We're going to do some problems. First off, we're going to start with this example of repeating decimals. And I don't know if you ever realized, do you guys know how to find out what this decimal is equal to? Do you remember how to do it? No, I won't do it. Without a calculator. Well, you know what? It's a geometric series. Let's write out some terms and see why I say it's geometric. Do you remember what geometric is? Look. Okay, do you remember what a geometric series is? It's the summation n equals 1 to infinity of AR to the n minus 1. So why do they start with n? Why do you use n minus 1? If n is equal to 1, this is AR to the 0 plus AR to the first plus AR to the second. And it doesn't matter when you get to infinity, 1 less than infinity is still infinity. 1 less than infinity is still infinity. You could also write it here. If you don't want to start with 1 and you want to start with 0, then this would be AR to the n. It doesn't matter. They're both the same. And this is equal to AR to the 0 plus AR to the first plus AR to the second. Still going off to infinity. Now, that's a geometric series. It's an exponential. So that's how I recognize it. The other way I recognize them is to write them out. Write out the terms so we can see what they look like. And when will this converge? A geometric series will converge when? Do you remember? S is equal to what? Do you remember the formula? If you haven't done it over the weekend, you should have, or you should have been in to see me this morning. A over 1 minus R, where A is your beginning value, that's A, and R is your common ratio. To get from one term to the next, we multiply by R. This converges only when R is what? Right, it converges if R is between 1 and negative 1. Won't converge at 1. Okay, Ori? And we'll do some problems. Now, last week, I showed you why it's this. Go look at the video again if you want to see the proof of why the sum of an infinite series is A over 1 minus R. And let's quickly look at, for those of you who don't believe it, what if I do 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 16th. And let's look at that geometrically to see if it converges. I'm just going to take a square. There's my first one. Then I'm going to take another square, and I'm going to take half of it. That's this. And then I'm going to take what? A fourth. And then I'm going to take an eighth. And then I'm going to take a 16th. What's happening here? Then a 32nd will be here. It's approaching what? 2. That's just the geometry. So yes, this converges. We could use the formula. S equals A over 1 minus R. What's A equal to? 1. What's R equal to? How do I go from 1 to 1 half to 1/4? If R is equal to 1 half. Try that again. So using the formula, it's 1 over 1 minus 1 half. You're not very good at fractions. This is what I do, and you're going to want to do it when you get to these crazy things. I'm going to multiply by 2 over 2. Okay? Question, guys? Do you see that? If I keep adding half of what's left in here, it will converge to 1. I'll show you, if you want to do it right now, we could go and look at the harmonic series and see why it does not converge using the same reasoning. A is the first term. Multiply to get there. Yes, A is just A. Right. Okay, doing the arithmetic, that's 2 over 2 minus 1, so it's just 2. Now, would you like to see why the harmonic series does not converge? And then we can come back and do this. Series. Some of the, remember, what's a series? It's adding up all the elements in the sequence. Sequence is the list, and then you can add up the elements in that list. So I could talk about the sequence of students in here, and then we could add you all up. Would you say, let's think of the 12 days of Christmas. Partridge in the pear tree the first day. What's the second day? 2 turtle doves and a partridge in a pear tree. So that's a partial sum. So on day 1, write it down. Day 1, you get 1 gift. What about day 2? You get 1 plus 2. Okay, that's the second partial sum. What's day 3? Well, you get a partridge in a pear tree, 2 turtle doves. Is it 3 geese a laying? Right? Okay. Yes. This is not geometric. Exponentials. This is not exponential. Okay, guys? Guys. So this is this is the third partial sum. That's S sub 3. Guess what? You get another sequence. What's the fourth day? 1 plus 2 plus 3 plus 4, which is 10. That's S sub 4. But really, what do you get all together? Total. Could you sum the partial sums? Could you add? You will add these all up. Because after day 2, how many partridges in a pear tree do you have? No. Day 2, how many partridges do you have? 2. And then 2 turtle doves. After day 3, how many partridges do you have? 3. And then you got 2 more turtle doves. It's like Issa Lane. I have to sing it to know it. No. The limit of the sequence has to go to 0 for the series to converge. This sequence is not going to converge, is it? If you kept going, but there's only 12 days, thank goodness. Otherwise, you're going to, and how many partridges in a pear tree will you have at the end of 12 days? 12. Okay, do you see how you can sum this up? So now you're summing up the sequence of partial sums. I don't think so. Right, that's not S. That's not A sub n, no. That's S sub n. These are S's. Okay, should we skip ahead to the harmonic series and see why it does not converge? Kind of cool. So I have to go to my last page here, which is right there. Now, if you don't concentrate, Grant, you won't get it. Okay, you guys, I'm going to write out a bunch of these. This is on the last page. Because it's really kind of cool. We're going to come back and do those. Is that okay? I'm not going to leave those. I'm coming back. Okay. Okay, you guys. I just wrote a bunch of terms down. Now, it's kind of like the squeeze theorem, but going the other way. It's a comparison. Okay, you guys in the back? It's kind of an interesting little way to look at this. So, I have a whole pi. No, this is not converged. This is the harmonic series. Let's look at it. Okay, so this, no. Now, I'm going to compare it. I'm going to show you a different series that diverges, but this is bigger than that. Okay, did you guys hear that? I'm going to write up a different series that's smaller than this and prove that it diverges. So it's 1 plus a half, and then I'm going to make this a fourth plus a fourth. Now, just looking at those terms, I'm writing a different series. How does this compare, the red compared to the black? Is 1/3 bigger than a fourth. So if I can show that this one diverges, then that one has to diverge. So the comparison test. If this one's bigger than this one, Grant, this one's bigger than this one, if I can show that this diverges, then this one would have to diverge, right? Does that make sense? I can compare it to anything I want. And I can show you I can get this one to diverge. Okay, so what I'm going to do now is add in an eighth plus an eighth plus an eighth plus an eighth. Do you still agree that the red is bigger than the black? Okay. And then I'm going to do a 16th plus a 16th plus 16th. How many of these 16ths am I going to have? 8, right? No, I got nothing. I have no idea, but it doesn't matter. Okay, guys, watch. Watch. Grant, do you agree that the red one is bigger than the black one? And if this doesn't converge, if this diverges, wouldn't that have to diverge, Grant? Okay, this is 1 plus a half plus a half. So guess what? Right here I've got 2. Right? Then this is what? 4/8 is a half. And this is 8/16, which is another half. So I've now got 2 plus another one. What's happening? It's getting bigger, isn't it? It's not going to converge. Because the next one I'll have 30 seconds, and I'll have 16 30-seconds, which adds in another half. And then I'll have, what, 64? And I'll have 32, which is another half. Do you agree that this black one is getting bigger? I keep adding in halves. This is bigger than that. So if this one diverges, what has to happen to that one? Okay, you did another convergence test called a comparison test. So I think that's kind of cool. If you do 1 over n squared, you could probably I could show that it's less than something that does converge. I haven't thought about it, but maybe I'll think about that for tomorrow. You could do that, but that takes time because that takes some thinking, doesn't it? I mean, well, at first I'm looking at this, I'm going, okay, well, this, I tried to add those up, and I go, oh no, let's make them an eighth because I know that's going to be a half. And this is clearly bigger than that. 1/5 is bigger than an eighth. So I know that if this diverges, that's going to have to diverge. You'll compare it to something you know. You'll see when we get there. It's not till 8-3 or 8-4, so don't worry about it yet. Okay, I thought that was kind of a neat little proof. Not for a while. No, because it's not geometric. That's a good question. Now on the test, guys, the only ones they'll ask you for values of are going to be geometric ones. So if they say find the sum of the series, you know it's geometric. This one diverges, so that diverges. That's all I was doing, showing it diverges. Now, do you believe the harmonic series is divergent? You might not have believed it before. That's it. It says show that it's divergent. I just did it. Now, you guys, what's the limit of 1 over n as n goes to infinity? Guys, Eric, shh. This is 0. That's not enough. It's required for this limit to be 0, but it won't make my series converge necessarily. I'm sorry, what? True? Now, if I do 1 over n squared, it goes to 0, and the summation of 1 over n squared does converge. What it converges to, I don't know. I'll have to look and see what I can find out about that. Okay, so let's go back now and do some problems. Okay, we want to do this problem, 2.317 repeating. No, we're going to do them right now. I'm going to add a page. Okay. That's a guys, you have 4 weeks. 4 weeks before we have break. So, now, that's geometric. You may not see it's geometric. Let's write it out. Okay. This is the same as 2.3 plus, and it's 0.017. Let's write it this way so I don't lose you. Don't lose me too. Okay, Grant. There's 1 in there. Etc. That's what that is. The 2.3 is not geometric, but this is. This is 17 over what? No. Tenths, hundredths, thousandths. In fact, let me write it this way. So 2.3 plus 0.017 plus 0.00017 plus, I have enough zeros. Wait, do I have enough zeros there? I don't think I do. Am I good? Oh, that's right. No, I want 1/7. Just the 17 repeat. Okay. Hey, did I do it right, you guys? Close enough? We're doing this problem. Okay, guys. Yeah, it's only good enough. But that's plus 17 over, I'm going to add 2 zeros there. Is that okay, Sam? Plus 17 over, how many zeros? Oh, I don't have enough zeros there. 5, 6, 7. Okay. The 2.3 is not a big deal. It's a constant. We just add it in there. But what's this going to be? What's A equal to? 17 over 1,000. What's R equal to? How do you get from here? 1 over 10 to the what? No? Second, because what's the repeat? Repeat is 2. The repeat was 3. It would be 10 cubed. There it is. So just the repeating part is A over 1 minus R. Is my R value between 1 and negative 1? Yeah. So it's 17 over 1,000 over 1 minus 1 over 100. What do you want to multiply by? Bigger. How about 1,000? Because I want the thousands there to go. I don't want any of this stuff. So that's equal to 17, and that's 1,000 minus 2 zeros cancel, 10. So 17 over, oopsie, 17 over 990. And then that's just the repeating part plus the 2.3. So you have 2 and 3 tenths. So 2, 2 and 3 tenths is 2 plus 3 tenths. That's what that fraction is equal to. Yeah. I gotta get this. I'm gonna multiply this by 99. Whatever that is. Yeah. Now that's, guys, you've missed a lot of time. You can't be missing this too. This is 100. That'd be 300 minus 3. What's 300 minus 3? You guys ever do that? 97 plus 17 over 990. Will my calculator give this to me? I don't know. What is this going to be? 14. Did I do my carry right? And that'll reduce. Yes, plus. Yeah, it doesn't look, looks like times. So it's 2 and, well, I assume I did my arithmetic right, but I'm not positive. Minus 3. Oh, I did this in my head. No, no. Yeah. I did 100 minus 1, and you're going to do it times 3. Yeah. Now, let's get my calculator out. I'm going to use it on something else anyway. Let's see if it'll give me the fraction. It should. Ugh. I hate that. Okay. Okay, so it was 2.01. Have I got that wrong? No, 2.317. Let's see if this will do it. And then we're going to go to math and see if it'll change it to a fraction. So I have 1147 over 495. Okay, you guys, what's half of, okay, guys, divide that. Can you guys divide that? You guys need different places to sit? What's half of that? What's 2 times that? 10, 18, 19. Yeah, remember that? So it's 157 over 495. What's half of that? It's half of 314. I did do it right. Yay. Okay, so you can find repeating decimals. You have homework problems that have you do this and write them as fractions. Now, they could ask you this question. You could do it this way. There's other ways you could do it as well. Oh, we haven't gotten anything fun yet. Yep, next part's fun. No, not this one. No. Oh, this is fun. Now, this is a geometric series, and x is a variable. When will this converge? Because if you write this out, this is what? If n is 0, then it's x to the 0. Then it's x to the first, plus x to the second, plus x to the third. Okay, shh. Ready? Now, I have an x there. It converges when x is what value? Geometric, isn't it? What's the a value? What's x to the 0? 1. Now, what's the common ratio? You're timesing by x. So r is equal to x. When does this converge? When x is between 1 and negative 1. Remember, the common ratio is between 1 and negative 1. Okay, granted, if you pay attention and do this, it's a lot easier. Now, what is the sum equal to? A over 1 minus x. So what's A? 1 and, sorry, R. What's the R value? It's x. So what they're saying is that this infinite series is equal to 1 over 1 minus x, provided that x is between 1 and negative 1. That's what it is. But this is what kind of a function? If it's a fraction, you remember what they're called? It's a rational. What happens at 1? What happens at 1? I get 1 divided by 0. Can't do it. Now, this is what we're going to be doing. This is called a power series. This is going to be one of the most important ones you're going to be dealing with. You still haven't seen exactly what I'm trying to show you. Okay? Okay, Duncan? This rational function can be written as the sum of those powers. And those I can take derivatives of and integrate so easily. This is not so easy to integrate. I get the natural log. I get a negative natural log of 1 minus x. I have to tell you that. This is very easy to integrate. This is x squared over 2. That's x cubed over 3. X to the 4th over 4. It's very easy. That's what we're going to be doing in the second half of the chapter. And what I'm claiming is if I graph this power series and I graph that rational function, they are the same things, provided that x is between 1 and negative 1. Now, do you believe me? Yeah. Well, that's pretty good. I shouldn't believe everything I say. So let's go ahead and put it into our calculator and see. Okay, so in here I'm going to put in, I'm going to clear, okay, 1 over 1 minus x. That's easy to put in. No, it wants that. Sorry. It's different this year than it has been, so it drives me nuts. Okay, clear. That was one problem. 1 divided by 1 minus x. Now, do you guys want to see how to use sigma in here? Now, if you don't have sigma, you just have to type in 1 plus x squared. But there's a sigma button here. Do you want to see it? Okay, so I go alpha. There it is, 2. There's my sigma. I better be in pretty printer. It won't work. I am. And we want to start with, no, I want to, this is a counter. Let's make it alpha n, starting at Where did we start at? No, we started at 0. And how many terms do you want to go to? 10? 100? A lot. Let's just do 10. And this is just x to the n. It's just x, right? Yes, it's x to the n. X to the n. I want that. Arrow. Alpha n. And we will zoom it 4. There's my rational function. Now here comes my polynomial. It has to calculate that. I made too many terms. Oh, there it is. Okay, let me do it so you can really see it. I'm going to go to y equals. I'm going to change this. Should we make this the little circle trace? And we know it only converges between 1 and -1, so why don't I change my window to -2 to 2. Okay, there's my rational function. Now here comes my approximation. It's an approximation. Remember, it doesn't converge unless you're between 1 and -1. I only did 10 terms. Well, it's going to be a little off because I have to do how many terms to be exactly right? All of them. However, in the field of, I believe it's biomedical engineering, when they're working with their machines, they don't work with 1 over 1 minus x. They work with these polynomials, like here, and they don't do very many terms because it's good enough. And that's how they work with it. And one of my told me that's what he was doing in the field of medicine, using these power series, which is very cool. If you were going into computer science, you'll be doing a lot of stuff with power series. And probably physics as well. There's a whole bunch of kind of series you can do. We're going to do Taylor series, but there's Fourier series as well. We won't do that. I don't even remember it. Okay. So this should be incredible to you if you think about this. This does not behave nicely. It has a vertical asymptote. That has nothing wrong with it. Okay, Grant? This is what we're going to be doing, just as a foreshadow there. Okay, now for the hard part. This is called a collapsing sum. And what you are going to end up finding out is that this will converge. Well, let's show it converges. And let's find the value. Okay. If you don't pay attention, you're going to have some problems here. This is called decomposition. Now, why do we have to know it? Because it's on the exam. You're going to have to be able to integrate that. Do you know how to integrate 1 over x times x plus 1? A u substitution won't do it. So we have to know another way. This is the result of adding 2 fractions. It's called decomposing fractions. It's in your appendix. Okay, you ready? Well, this is not a good time. Okay, let's just focus on this part right here. Now, you haven't seen this before. This is after you add 2 fractions. These are only for linear factors. These are linear. They're just x's rather than x squared. So they're linear factors. It's a over n plus b over n plus 1. And I'll show you the easy way to do this. The book doesn't do it the easy way. So we added 2 fractions, and we got this answer. The question is, what fractions did you add to get that? Because if I could break this back into 2 fractions, couldn't I integrate this one and integrate that one? Do you remember what that would be? What's the integral of 1 over x? ln plus c. Okay, Grant, don't even come in to see me. Seriously, you haven't paid any attention all hour. No, but this is tough. It's not really that bad. So all I want you to realize what we're going to do is we're trying to figure out what fractions we added to get that. So what we're going to do is clear out the fractions because that's the easiest way to do it. So I'm going to multiply everything by the least common denominator. And then we're going to be clever. And the book is not clever. But we are more clever than the book. Okay, Eric, what am I going to get from the first one? What's going to cancel out? So I'm a times n plus 1 plus, what cancels here? The n plus 1's cancel. Ori. So it's b times n. And what cancels over here? Everything. You will have to do this on the AP exam. We'll be in the multiple choice section. Doubt that it would be in the free response. So this is equal to 1. Now, n represents any number. And what I want to do is find the values of a and b. That's right. That's right. Now, what the textbook does is it takes different values of n. It says let n equal 1, and then you get a system of equations. And let n equal 2, and then you can solve it. But it's easier than that. Ori looks ahead and says, what if n is 0? What if n is 0? Because n could be any number. Then this is a times 1 plus b times 0 equals 1. So a equals what? 1. What's another nice value? You can put anything you want in for n. Negative 1. Because if I put in negative 1, this first term is going to go away. So it's a times 1 minus 1 plus b times negative 1. And when you do the collapsing sums, 1 will always be positive, 1 will always be negative. So b is equal to a negative 1. And if you don't believe me, you can add these fractions. Let's go ahead and rewrite it. This is a, which is 1 over n. Sorry, I want to keep it so I can see it. And then b is negative 1 minus 1 over n plus 1. If you were to add those fractions to get common denominators, you would end up with 1 over n times n plus 1. Do you believe that? Well, we can do it. We can do it. Now I can integrate it. Is that equal to 1 over n times n plus 1? Okay, what are the common denominators? Eric? What do I multiply this one by? N plus 1 and n plus 1. What do I multiply this one by? N. So I get n plus 1 from this one over n times n plus 1. I'm going to have a common denominator. Minus n over n plus 1 equals 1 over n plus 1. Is that true? Yeah. It's a method to find what fractions you added together. I let n be any value I want. Could I have used 10 and 20? Yes. But then I would get a system of equations. Then I have to solve my system of equations. This is much easier. Okay, so here's what we got. We have this. We're not done. I want to make sure I have this right. We can find these. We can find this sum. And why do you think it's called a collapsing sum? Because it collapses. Let's go ahead and put some values in. Now, I'm actually going to make that, let's call that I, or what? Oh, I don't want to do that. I'll make it go to infinity. But I want the limiting value. So when n is equal to 1, I'm going to get 1 over 1 minus 1 over 2. What if n is equal to 2 now? It's 1 over 2 minus 1 over 3. You're going to see in a moment why we call it a collapsing sum. And then it's going to be plus 1 over 3 minus 1 over 4. Plus 1 over 4 minus 1 over. And the n ones are going to be 1 over n minus 1 over n plus 1. What are the ones right before it? What's the one right before 1 over n? 1 over n minus 1. And what's the one right before this one? 1 over n. So you can see what's going to happen. Now what happens? Now we're going to take the limiting value of this eventually. Well, what happens? These guys go. That's right. And then these go. It's what's called a collapsing sum. I need this to prove the fundamental theorem of calculus. We use a collapsing sum. So everything goes, and this is going to go with the one before it, right? This is going to be there. So I'm not going to be left with 1. I'm going to be left with 1 minus 1 over n plus 1. But I'm going to take the limit and let n go to what? Infinity. That's right. What is that? What is this limit? Because I'm going to add this up an infinite number of times. This is going to go to 0. So this answer is just 1. No, I said the limit as n goes to infinity. Can't miss a word. Because this didn't cancel out, did it? This sum ends up being 1 minus 1 over n plus 1. Yeah, so if n is equal to 4, you got 1 minus 1/5. But I want n to go to infinity, so it's going to be 1 minus 0. It's 1. That's the value of that sum. Now, they're not going to ask you this. Guess what this equals? It equals 1. They will not ask you for the value of a collapsing sum. I've never seen it yet. No. Now, I would like to answer a couple questions still. Oh, so let's do 9. We haven't done number 9. And I didn't tell you about the properties of sigma, that if you have the sigma of A plus B, that's this. So guess what? We can do this quickly now. Ready? This is the same as this. This is not geometric. That is not geometric. And you had some problems. In fact, we'll come to that problem in a second after we do this. Now, here's another thing you can do with sigma. If you have some constant times A, you can pull this constant out in front. So I can pull this 3 out in front. And we just found this sum, didn't we? What was that sum equal to? 1. Okay, so this is 3 times 1. Does anybody recognize what this other series is? Now, for this big series to converge, both must converge. But you recognize that? Well, if you don't know, let's write it out. 1/2 plus 1/4 plus 1/8. Remember, if I'm asking for a value, it must be what? It's not harmonic. No, it starts with 1. Is it 2? It's not starting at 1. Starts at 1/2. But you recognize this? It's geometric. So what's your A value? What's your R value? 1/2. So it's A over 1 minus R. So it's going to be plus 1/2 over 1 minus 1/2. Well, that's 1/2 over 1/2. So it's 3 plus 1, which is 4. Got to be careful where you start. That counter matters. Yes. because I just taught it for you to you. I'm just saying we are going to decompose this and figure out what fractions we added. I'm sure that's what somebody did. I figured it out without reading the book. Yeah. Now, these are only true if these are what they call linear factors. If I have n cubed here, this method doesn't work. No. It's geometric if it's like 2 to x. Exponential, it's geometric. So, tomorrow we're going to do improper integrals. So the question I have for you is how did you do 23? Okay, not time to go, you guys. We got a couple minutes. Now, have a seat. I'll bet you didn't get this one. Some of you might have. What is the first thing you should do is see if the limit of the sequence is 0, and it is, because this is what you have to do with this one. You have to divide this. It's 1 over 3 to the n starting with 1, not 0, plus the summation, n equals 1 to infinity of 2 to the n over 3 to the n. How about if I wrote it this way? This is 1/3 to the n. What's special about that? It converges. Why? It's geometric. No R value unless it's geometric. Then this one, will this converge? Because you know what this one is too? It's 2/3 to the n. And so your R value is equal to 2/3. This is geometric as well. Now, had this been 3/2, you say it diverges. For a series to converge, everything has to converge. Whew. So tomorrow, I have to cut out of here early, but tomorrow we will do the improper integrals. With that, you have to remember how to integrate. That's all. That's all.